Welcome to 23rd lecture. We are studying stochastic processes and Markov processes, and for the last couple of lectures we have been studying steady state behavior of Markov chains. Right. So before this lecture, in this lecture we'll solve an example related to the steady state probability of Markov chains. So before this, there is a small recap, and that is that the long-term probability or the steady state probability as n is very large of being at state j in a Markov process is equal to the summation over all states in the state space probability of going from k to j from n minus 1 to n times the long term or the steady state probability of being at state k at time n minus 1. Right. And we have also studied that these states, the asymptotic behavior of these states is such that they tend to convert their self at one value of the probability, both any value, any Ri tend to settle itself at a value, at a constant value. So you will see a kind of saturating behavior for all for all for all pi j's, for all pi j's or pi i's. As the n increases, they tend to saturate, they tend to settle at a value, at a constant value of probability, provide there is only one RC recurrent class in the chain, and there are no transient states. Right. So this is the recap of our last lecture, or a last couple of lectures, in fact. In this lecture, we'll solve an example where an absent-minded scientist has two umbrellas and he has to compute between his residence and his lab. And these are his two umbrellas. Right. And if he is at his residence, he goes to his lab, and if there is raining, he takes one of the umbrellas, provided there is one umbrella at his residence. And the same is true about him when he is in his lab. So he takes an umbrella only if it is raining. If it is not raining, he forgets to take the umbrella. So if he is in the lab and it is not raining and he has two umbrellas here, U1 and U2, they both are here, and it's not raining, he'll go to his residence without taking an umbrella. And when he'll be at his residence, he'll be without an umbrella. And if tomorrow he has to go back to his lab and there is no umbrella here and it is raining, so he has to be wet. Right. So it rains with probability 0.7 in his region where he lives and where his lab is located. So what's the chance that he will be wet during a commute? Right. He will be wet only if it is raining. If it is raining and he has no umbrella at his place, whether he is at his residence or he is at his lab, if he has no, either if he's at his residence or is in a lab, if it is raining and he has no umbrella at his place, at his current place, he has to be wet. Right. So here is a Markov chain that we can draw. We can draw for it. Markov chain contains it contains three states, where state number 0, 1, and 2, they represent the number of umbrellas at scientist's current location. So if he has 0 umbrella and he has 2, then he's moving, he will definitely be moving to a place where he has 2 umbrellas, because if he is in his lab or he's at his residence and he has no umbrella over here, so he'll definitely be moving to a place where he has 2 umbrellas. And it's not the chance of his getting wet, because it can be raining or not. If it is raining, he's moving from a place where he has no umbrella and it is raining, only then he will be wet. If he is moving from a place where he has no umbrella and it is not raining, he will not be wet, right? So if he has at a place where he has 2 umbrellas and it is raining, it rains with probability 0.7. So he will take an umbrella and will reach to a place where he has 1 umbrella. And if he has 2 umbrellas and if it is not raining, he'll move to a place where there is no umbrella. And same can be interpreted about state 1. If he has 1 umbrella where he currently is, and if it is raining, he will take the umbrella and will reach to a place where he has 2 such umbrellas. So it contains one class of recurrent states, and that class is also aperiodic. We cannot divide it into further subsets, and all arrows from one subset are moving to the other subset. This is what we studied in last lectures. So the class is not periodic, it's aperiodic. We cannot divide it into sets where all arrows from one set are merging out to the other set. State I, right, and then we can apply the same recursion-based formula that we studied in 3 or 4 lectures before to find the steady state probabilities for all 3 states. Pi 0, the same is implemented for pi 1 and for pi 2. The simple mathematics, we have been studying this recursion-based formula in our last few lectures. And the interesting thing is that the first equation gives us pi naught equals 0.3 pi 2. The second equation gives us pi 1 is equal to pi 2. And the third equation gives us that pi naught is 0.3 pi 1, right? So the equations are not independent, because pi 1 is equal to pi 2, but pi naught is 0.3 pi 1. This means pi naught is equal to 0.3 pi 2. So the equations are not independent. So what we have to do is, we have studied before that we'll apply a normalization theorem, that sum of all the steady state probabilities of these 3 states would be 1. So putting that equal to 1, and pi naught is 0.3 pi 1, and pi 1 is pi 1, pi 2 is pi 1. We have derived that pi naught is 0.3 pi 1, pi naught is 0.3 pi 1, pi 1 is equal to pi 2, and pi 1 is written as pi 1. So we get a value of pi 1 over 2.3, and since pi 1 is this, pi 2 is also, this is pi 2, not pi 1. This is pi 2. So pi 2 is also the same as pi 1, because we have derived it that pi 2 in this case is equal to pi 1. And pi naught is 0.3 times pi 2, so 0.3 over 2.3, right? So probability that the scientist gets wet is pi naught times the probability of raining. Pi naught means he has no umbrella at his current place and it rains. Only then he can be wet. If he has no umbrella, and if it is not raining, he won't be wet. So he has to have no umbrella at his place of residence, and it must rain. Only then he can be wet. So multiplying these two gives us 0.091. That's all for this lecture. For upcoming lectures, we will be studying more about Markov chains. Thank you.